I'm Charles McKay. I'm the Dean of the School of Science and Computer Engineering at the University of Houston Clear Lake. On behalf of our president, William Staples, who unfortunately broke his ankle last night and therefore is unable to be with us today, I want to welcome you to this program. I think it's going to be a very exciting evening, and I think that we're all looking forward to hearing what Dr. Gates has to say. First, however, I'd like to introduce you to a young man that I'm particularly proud of. He is Dr. David Garrison. He's the faculty chair and the assistant professor of physics at our university and within our school. David began his academic career at the Massachusetts Institute of Technology, where he earned his BS in physics in 1997. During his course of study, he minored in Earth, atmospheric, and planetary science, and he completed a concentration in political science as well. He then moved on to the Pennsylvania State University, where he completed a PhD in physics in 2002. After that, he accepted a position as a visiting assistant professor at UH Clear Lake. After serving as a visiting faculty member for 1 year, he was promoted to tenure track, and during his time in academia, Dr. Garrison has earned several prestigious awards from organizations including NASA, the Institute for Space Systems Operations, the Alfred P. Sloan Foundation, the Council of Graduate Schools, and the Texas Educational Grid Project, in addition to several internal grants and scholarships. During his time on the faculty, Dr. Garrison has served as the chair of the physical science and physics programs. He successfully developed and oversaw the approval of a master's degree in physics and a revised bachelor's degree in physical science. His research in computational and theoretical physics consists of work in numerical relativity and cosmology. Our own Dr. David Garrison.
All right. Thank you, Dean McKay. As Dean McKay said, I'm Dr. Garrison. I'm the chair of the UHCL physics program, and I'm proud to introduce tonight's speaker to you. We're honored to host a most distinguished physicist who will speak about future discoveries that we will have a chance to see that will really change the way we see the world. But first, I'd like to tell you about our physics program. The UHCL physics program officially began operations in the fall of 2004 and began offering for the first time in UHCL history a master's degree in physics. The purpose of this degree is to broaden the technical backgrounds of practicing physical scientists and engineers and to prepare students for doctoral study and advanced research in physics, astronomy, space science, and related fields. In 2005, we added a professional physics subplan, effectively broadening the mission of the program to include the training of technical managers using a combination of physics, systems engineering, and management courses. As our physics program continues to grow, we also broaden our base of community support. It is this support that helps strengthen our program at UHCL. In fact, we have community support to thank for bringing tonight's speaker to you and for supporting the continued growth of the physics program. It is with great thanks that I recognize the following benefactors of tonight's event. Our event underwriter is the UHCL Office of the Provost. Our reception sponsor is MEI Technologies. Our promotional sponsor is Ron Carter Automotive Dealerships. And our general sponsors include the Boeing Company, the Council of Graduate Schools, Alfred P. Sloan Professional Science Master's Grant, and Endeavor Condominium. I would also like to thank those who helped make this event possible at UHCL, the Office of University Advancement, Dion, Joanne, and Andrea. And now for our speaker. A great scientist once told me, doing physics is like learning how to play an instrument. You first need to learn the scales. Professor Sylvester James Gate, Jr. was that scientist, and I am honored to be introducing him tonight. Professor Gates has a number of firsts to his name. His doctoral dissertation at MIT was the first ever at that university on supersymmetry. In 1991, he was the first director of the NASA-supported Center for Atmospheric Studies at Howard University. In 1994, he was the first recipient of the American Physical Society's Edward A. Bouchet Award, given to a minority physicist who has made significant contributions to his field. By the way, Edward Bouchet was the first African American to earn a PhD in physics or any field in the United States. In 1998, Dr. Gates was named the first John S. Toll Professor of Physics at the University of Maryland, and he became the first African American to hold an endowed chair in physics at a major U.S. research university. In addition, Professor Gates was one of the first African American physicists which I met while I was a student at MIT. In addition, Professor Gates authored or co-authored over 120 research papers and co-authored a book. He has held appointments at MIT, Harvard, Caltech, the University of Maryland, and Howard University. He has been profiled in newspapers such as the Washington Post, Orlando Sentinel, and the Memphis Commercial Appeal, and the Sunday supplement of the USA Weekend, and has provided comments on scientific stories in the New York Times, Washington Post, and USA Today. To date, he has appeared on 4 PBS television scientific documentaries: The Path of Most Resistance, Mysteries of the Universe, The Elegant Universe, and a new one, Einstein's Big Idea. In 2005, he spoke at over 30 national and international celebrations of the Einstein World Year of Physics. Tonight, he will tell us about some new discoveries which we hope to see in the next few years. Please welcome our distinguished speaker, Professor Sylvester James Gates, Jr.
Well, good evening. I always like to start a presentation like this out by thanking the people who invited me here. I extend this thanks to David, to the wonderful day I've had here from meeting with President Staple, Dean McKay, and a number of other people that make this place go. I told David that he's found an exciting place to grow, and this really is an excellent environment, it seems, where science can take hold and grow and flourish with people driving it to its very edge. Science is what I do. I fell in love with science as a child, probably around the age of 6 or 8, and I never lost that love. In fact, the American Association for the Advancement of Science has a new campaign where they're trying to put faces on science, and I was asked to contribute to that. And so someone asked me, what is it that I think of science, or why is science exciting? And my comment was that science is like the toy that never gets boring. Now, what in the world does that mean? Well, I still think I remember being a child and having Christmas come once a year. And sometimes you would indicate to your parent what toy you wanted especially, and maybe that toy was there under the tree. You'd get it, you'd be excited, you'd play with it, and play 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 and play. And then eventually that toy would sort of lose some of its appeal. It'd get boring. Well, you see, in my life, the doing of science is like finding that toy under the Christmas tree one morning, but it's never gotten boring. And in fact, I don't ever expect it to. So science is something that if you have a mind and a will and a heart to do, you find out that it keeps you young. I'm 55 years old. And many people, well, they can tell from the hair these days, it's starting to go to white. But in many ways, people think I'm a lot younger than I am. And the only thing that I can think that does that is the joy of being involved in something that I love. Well, tonight I want to talk about some boundaries in science. And in fact, we're going to talk about how Texas almost got there. That's going to be part of the story. But not quite, and it's not your fault. I have a image going here that I like to run for people. It shows a piece of science. And let me just say, I would be remiss if I also didn't acknowledge all of the images, the creator of all the images I will be using tonight. A young man by the name of Kenneth Griggs, who is one of our graduate students at the University of Maryland, is a person who put together all these images that I will be using. Now, normally, when you come to a talk like this, and it's physics, if you're a non-physicist, you might feel just a little bit of concern, because typically when physicists are let loose on the public, the first thing we tend to do is find a blackboard someplace and start scribbling the most unreadable and incoherent scribbling that we can think of. And then we turn it around and say, "Isn't that beautiful?" And of course, the general public looks at us and says, there they go again. But tonight, what I'm going to do is I'm going to be telling you about science and some of the greatest accomplishments that we have made in science and things that we see on the boundaries. But I'm not going to do it with the equations. And the reason I can do this is because of something very interesting about the development of computers. If I showed you a musical score, I don't think most people would be uncomfortable with that. It might look complicated, but we all know that music is something that we can have a direct experience. And so no one runs away from a musical score. But if I showed you a sheet full of integrals and derivatives and pluses and minus signs, a large fraction of the American public says, "Oh my God, let me protect myself against that." Well, you see, the way that we physicists use mathematics is kind of peculiar. We kind of use mathematics as a kind of score. And so when we write our equations, rather than saying, "Show me the score," what you should say if you're not a scientist is, "Let me hear the score." And the images that I'm going to show you tonight is the analog of hearing the scores that lots and lots of equations that people like me write are actually talking about. So this particular image here is one of I'm very fond of. And it shows a representation of a binary star system. You'll notice that there are these two balls that are rolling one around the other. Those are representations of stars. You'll also notice that there are striations around each of these stars that make them look sort of like beach balls or basketballs. Well, those are representations of magnetic fields. Stars have magnetic fields around them just as our Earth does. That's why our magnetic compasses work. And there's another feature here. You can see there are these beams that are shooting out the top, and they're actually also out at the bottom. If I stay at one location, every time one of those beams hits my location, I would see a flash of light. And in fact, this is a binary star pulsar system, and the way that we discovered these things is more or less what I just said about seeing flashes of light. Let me tell the story because I think it's interesting to see how accidents can push science forward. So let's imagine that you could go out one evening and look up at the stars, and you might see a bunch of flashes. So let's set this movie to working. Now, this actually happened in the 60s. In the 60s, our country was concerned about nuclear war, and we wanted to know what the Russians were doing about developing nuclear weapons. One way that you can find out such information without actually going to a place is by putting satellites up in the sky and looking down at the Earth for a burst of high-energy gamma rays. Because whenever you set off a nuclear explosion in the atmosphere, a burst of these rays goes out. And so in the 60s, we developed a series of satellites to orbit the Earth and detect these rays to find out if the Russians were exploding nuclear weapons in the atmosphere. Some of these satellites got out of alignment. And instead of looking down on the Earth, they ended up looking up towards the stars. And when that happened, well, we made a fantastic discovery. E.T. was testing nuclear weapons. Well, that's not quite what happened. We saw these bursts, and eventually we figured out that the bursts are natural phenomena. And in fact, they're the one that I just showed you. So we don't always see them in light. They may be in other parts of the electromagnetic spectrum where they occur. But if we could imagine going out and detecting them, we might see this. So let's go to that place. And so we have to travel through space and time. And here we are coming down along the north pole of the animation that we just saw. There are two stars orbiting one about the other. And you'll notice that stars are so massive they actually can bend space. And so these grid lines that you see represent the bending of space around the stars. And so here we are above the equatorial plane. That's the view that we first viewed as we came in. And as we view this, you'll notice there's another feature on this drawing that's very prominent. And that is, there is something that looks like water that's being pushed out of the way by these stars. Now, whatever this substance is, if we imagine it is water, we could go surfing. So let's imagine surfing these waves as they leave the stars and travel through space. One such wave might encounter a familiar blue marble and its companion, namely the planet Earth. And so this wave is going to come down from the heavens and strike the Earth. And let's imagine that we surf this wave to two places above the U.S., one in the state of Washington, the Hanford Reservation, and the other is just north of Louisiana. And if you broke through the clouds as this wave comes down, what you would see at a certain point would be a large L-shaped building, and there it is. Each arm is 4 kilometers long, which is over to 2 miles. And as you can see, the effect of this wave in this cartoon is that it's shaking this building back and forth. Now, when you walk outside of the door and you look at the buildings outside of you, you don't see them being shaken back and forth. And so you might say, well, Professor Gates, you just showed me a piece of science fiction. After all, Star Wars and Star Trek are always talking about waves and rays and all of these things in outer space, but they have nothing to do with our reality. So in order to set the right scale of the shaking, let me get rid of this cartoon and show you the actual size. This is a representation of a helium nucleus. The blue balls represent protons. The clearish yellow balls represent neutrons. And then in their interiors, you'll notice there are smaller pieces of matter. Those things are called quarks, and they were discovered about the time I was graduating in high school in 1969. We know that in the interior of protons and neutrons are these little tiny bits of matter. And now you'll notice there's one other feature in this drawing. There's this peculiar red line that you see extending across the image. And this line is not, in fact, a defect. In fact, I asked that Ken purposely put this here because I wanted to show you by how much the arms on that 4-kilometer-long building are stretching and shrinking. They're stretching and shrinking exactly the length of that, the thickness of that red line. That is 1/1000th the size of a helium nucleus. And so the LIGO facility, which is a real piece of science, you've, roughly speaking, as American taxpayers, spent about $400 million to build those two facilities. And their whole purpose of building those facilities will be to measure the shaking caused by that wave or waves like that coming from outer space, the 1/1000th the thickness of the atom. Now, that sounds like science fiction. In fact, our species has never had the kind of scientific capability to measure a distance that small. We are only now developing the technology for doing this. But we are underway, and this experiment has actually been underway for about 2 years. And if we detect these waves, something momentous is going to happen. You see, if we detect these waves, these will be the first signals from the heavens that our species has ever gotten that came to us by something other than electromagnetic radiation. Every single other fact that we know about what goes on in the heavens above us is brought down by light, radio, gamma rays, X-rays, and all of these are forms of electromagnetic radiation. This kind of wave here, well, I didn't tell you what it was, so let me reveal the secret. It's a wave of gravity. It's the last thing that Albert Einstein predicted in 1916, that gravity can behave like a wave. Now, we've never seen that behavior. We've never seen, if I were to take something and drop it, we don't see it wiggle as it falls. It just falls directly down. So it's kind of odd to think of gravity as being able to execute a kind of undulating motion. And yet, Einstein's 1916 equations predicts exactly that gravity can execute a kind of wave motion, and we're going to try to detect it. If we can detect these waves, then we will be able to view the universe in a new kind of astronomy. It'll be a little bit like going from black and white TV to color TV. Now, I know for most young people that this probably has no resonance with you, but when you get to be 55, you can remember the difference between black and white and color TVs. There's a lot more information in color TVs. Two shirts, one blue and one green, might be the same shade of gray in black and white. But with a color TV, you can distinguish them. And so these new kinds of waves, these gravity waves, will allow us to look at the heavens in a way that we've never had before. And in some ways, which I think is really beautiful, it will be as if we're hearing whale song. You probably have heard of whale song, that whales in the ocean create these songs that travel tens of thousands of miles that the U.S. Navy has been able to detect in the ocean. Well, the kinds of songs that these stars sing, if we are successful with this experiment, we will hear for the first time. So it will be as if we're hearing whale song from stars, light years and light years and light years removed from us. This is a new phenomena, and that's the kind of advance we get with science. Now, most of my talk is not going to be about cosmology and astrophysics, because this first part, those are the branches that are extremely exciting. There's a whole new generation of telescopes and instrumentation that have been put up by NASA over the course of the last 5 years and projected into the next decade that will allow us to look at the heavens with more fidelity, more detail, more insight than has ever occurred before. And so that's one of the frontiers of science that we just happen to be fortunate enough to be living through. That instrumentation would not be up there if it weren't for NASA's capable role in putting these kinds of scientific instruments into space. So the science done by NASA is among the most cutting edge that is present today for our entire species. And yet, of course, we see the agency beat up about all kinds of things. Those of us who love science have an appreciation of the science mission of NASA, which unfortunately looks like it's going to have to be cut back in our drive to put a man on the moon and then to Mars. But I'm going to tell you about a different frontier. The frontier I'm going to tell you about is the one that almost happened here in Texas, but it didn't. And like I said, it's not your fault. I'm going to talk about a ring. The title of my talk is Lords of the Ring, and we're going to find out who these lords are. But what I want to do, first of all, is, again, talk a little bit about looking back and then looking forward. I knew it was going to be a physics lecture. You know, you can't get a physicist in front of an audience without expecting him to shove some equations down your throat. So here's my little effort. These equations are, in fact, very important. These equations were written first in the 1800s. And in fact, we call these Maxwell's equations. But it's really odd because of these equations, Maxwell only actually added this one term right here. All the other terms in these equations were found by other scientists. Now, you'll notice also I call these the cell phone beeper equations. Because you see, this is the basis from which we derive the technologies of cell phone and beepers. You see, before Maxwell and the work of Faraday, no one imagined that there's a kind of wave that could travel from one place to another. But when you write these equations, in fact, one of their predictions is that such waves exist. Well, you're probably bored with seeing the equation, so instead, let me show you the picture that's associated with that equation. This is a picture of a charge. Now, what do I mean by that? Well, physicists often are confronted teaching students about electromagnetic phenomena. And so on day number one, we talk, there are these things called electrical charges. When I teach a course, the thing I say to my students is, when I say the word charge, I want you to imagine a spherical porcupine. So it's a ball, and it's got lots of hair that extends off in all directions, like a bad hair day. Now, one of the things about this picture of this hairy porcupine is you can imagine taking the porcupine and moving it, and then asking yourself a question, what happens to the hair? So this animation here is going to show us what happens to the hair. You'll notice that as the porcupine moves, and the porcupine is right in the middle here, the hair, in fact, doesn't instantaneously move with the porcupine, only the pieces that are attached to it. But the pieces that are far removed actually, let's watch it. So you see that wave going out along the hair? That's what happens when you take this spherical porcupine and start to shake it. The hair generates these clumps, these kinks, which then spread out along the hair. And that's, in fact, what that last term in Maxwell's equation tells us about the electromagnetic force, that it is capable of supporting a type of kink that travels outward and away from the location of the moving charge. That kink has a name. It's called a photon. You see, the hair around a charge is mostly invisible. You can't, if you actually could look at a charge, you might see a dot, but you wouldn't see all this hair unless you take the porcupine or charge and start to move it. Then, in fact, you would find photons streaming away. That's how we create light. And every light source, like the one shining down on me, we are taking millions and millions of charged particles, and we're shaking them back and forth. And what they do is wind up giving off these kinks in the electrical field line, which travel down, bounce off me, and allow you to see me. That's how we generate light. Before Maxwell's equations, we had no way to understand this process. We didn't imagine that electric and magnetic properties have a wave that can travel from one place to another. Well, after Maxwell's equation makes this prediction, a guy by the name of Heinrich Hertz came along and said, gee, you know, I'd like to check that mathematical prediction, because although I can show you this cartoon, it's also a set of equations I'm showing you. And so Hertz went to his laboratory to try to detect these waves, and he found them. Now, most people have never heard of Hertz, but I bet a lot of young people have heard of megahertz. That's not his cousin. That's not his child. Megahertz is his name with the word mega attached to it. And so we pay homage to Heinrich Hertz's work when we talk about the megahertz frequencies at which computers operate or radio signals operate. What we're talking about, by the way, is how many times per second, when you talk about hertz, you talk about how many times per second you wave the charge back and forth. That's what the hertz is all about. And so when we see science enters our life in every day, because most of us walk around, like me, tied to one of these devices. Cell phones, beepers, these modern communication technologies. And yet, if you don't know that these waves can move from a device like this to my wife, say, a couple of thousand miles away, you would never want to imagine dreaming of making such a device. And so that's what science does for us. Science is the way by which we find our most precise understanding of what our world is like. A lot of people are confused about science. A lot of students, when you ask them about science, they'll tell you, oh, it's what I find in my science book. The only problem with that theory is that it's like walking into the studio of a sculptor, looking down at the floor, and concluding that sculptors are people who turn big rocks into little rocks. In fact, you've missed the entire point of the endeavor. It's the sculpture. In science, it's the uncovering of the facts that we're about. The facts themselves are kind of the pebbles that are left on the floor, and yet that's how we, in fact, build our technology. It's based on those facts. Another confusion about science is that science is the search for truth. That's not the case in my opinion. What science is really about is making our beliefs about nature less false. You see, in science, when we find something like this picture of Maxwell's equations, we give this a name. We call this the theory of electromagnetism. Now, why the word theory? Well, you see, in science, we must face the fact that humans are limited in our knowledge and our ability to know things. And so when we perceive something about the universe, the best thing that we can do is say, this is what we think based on the evidence now. But that means that you must leave open the possibility that you are wrong. And so science is not about truth. It's about making our beliefs less false. These are not the same thing. And this often confuses people about science. So these are things that we have found out in the past about the world, that this process has led us to understand that we can build technologies like the manipulation of electromagnetism, which we use to our advantage a lot today. But of course, science didn't stop with electromagnetism. In fact, Albert Einstein came along and looked at these same set of equations and said, you know, there's something funny going on here. If you compare these equations that Maxwell writes to the equation that Sir Isaac Newton writes, the two sets of equations are not harmonious. It is as if, in fact, the way to think about what's going on is that Newton writes one score of music. Maxwell writes a different score of music. When the one score is played by itself, it sounds very beautiful. When the other score is played by itself, it sounds very beautiful. But when you play the two scores together, there's a dissonance. Einstein was the person who first heard this dissonance most acutely. And that's why Einstein was able to do something that no other physicist had done, to understand that, first of all, that this dissonance was there, and then secondly, he was able to remove this dissonance. And the way that he does it, or did it, totally remade our view of how the universe is put together. What Einstein teaches us, for example, is that space and time are not separate. They are part of each other. For those of us who are physicists, we express that by saying time and space are a part of something we call a vector. Now, in electromagnetic theory, these E stand for electric fields, the B stand for magnetic fields. Einstein also taught us that these E's and B's are actually part of simpler objects, which also, interestingly enough, there's one time and three spatial direction. Einstein observed that in electromagnetism, there's one object called the scalar potential, another object called the vector potential, and it's a 1 and 3, just like space and time. In fact, he kind of uses electromagnetism to figure out how space and time work. And by this method, he removes the dissonance, because he says there's one set of harmonies that control both the laws of space-time and the laws of electricity and magnetism. And we call that the theory of special relativity. That's what he was doing, and starts off with his wonderful work of 1905. Well, science doesn't stop there. We've been using these insights to move our technology forward. And now let me tell you about some strange things about our universe that puzzle us in more recent times. So in this one, I'm going to ask these let me set up for you an experiment. Let's imagine that I had two flashlights, and I could shoot light beams out. Instead of actually watching the light beams, I can actually watch the kinks. Remember, light beams are actually kinks in the field lines. And so I've represented those kinks here as little balls. If you actually take two particles of light and shoot them at each other, what you will find is that they'll pass right through each other without affecting one the other at all. They simply go right through each other. Now, that's interesting because you see, in fact, right now there's a piece of science that's trying to take advantage of this fact. You've all heard of computers because, that's how we mostly make our living these days, a lot of us, by interacting with computers. Well, there's an effort right now to build a new kind of computer called a quantum computer. And the quantum computer is based on the fact that if you take photons, they are allowed by the laws of nature as we understand them to become entangled as they pass through each other. So when they come together, somehow they trade properties and keep a memory of that trading as they move apart. And so there are groups of scientists right now trying to use this effect to build a more powerful, a faster, a better type of computer, something called a quantum computer. However, there are things in nature that don't exhibit that behavior at all. Suppose, for example, I took two electrons and shoot them directly at each other. In fact, they don't touch. They repel each other. Remember high school physics? Like charges repel? Well, here we see it. Like charges are being repelled here. Now, the repulsion that we see here is actually very important because, you see, that's the reason why you can sit comfortably in your chair. Because what's happening essentially is that there's an electrical repulsion between the electrons that are parts of your body and the electrons that are in the chair under you, and it's that repulsion that's supporting you. That's why we can walk around on floors, we can't pass through walls. Those forces are mostly electrical in nature. But it turns out that our world is such that if you were to turn off these forces, the electron would still show this behavior. And the reason they do so is something very strange. You know, in the real world, we know no two things can occupy the same space at the same time. Well, in quantum mechanics, this gets translated into something called the Pauli exclusion principle. And it's a statement about a certain mathematical rule that no two electrons can have all attributes exactly the same. Location, by the way, is an attribute of an electron. And so that's the basic explanation for why this repulsion occurs, is that electrons are very different from particles of light. Now, electrons also have another property. They behave like little spinning balls. And they spin on their axis. But you can't speed them up, nor can you slow them down. They always spin at the same rate. And we physicists call that h-bar, or actually 1/2 h-bar. On the other hand, photons also behave like spinning balls, but they spin at twice the rate of the electrons. So they spin at a rate of h-bar. And so it seems to be the case that when you get things that spin at 0, 1, 2, 3, or 4 times h-bar, these are objects that without charge are allowed to pass through each other. But if you have an object that spins at 1/2, 3/2, 5/2, or any odd multiple of a half times h-bar, these are objects that all have the intrinsic property that no matter what you do, they have to repel each other. Now, that's a very interesting attribute to know. Why is nature like this, where the things that spin at half rates are, in some sense, have an intrinsic repulsion, but integer spin things don't? Now, this repulsion is actually very important. You've probably had high school chemistry at some point, and remember these things called orbitals. I have nightmares still about that. So here's an atom with a bunch of orbitals about it. And you see these funny shapes that are maintaining, because these purple blobs represent the clouds of the electron around an atom. The property that maintains this is because of this intrinsic repulsion that I told you about. That's part of the explanation for why these shapes are there. So now, remember, I told you that physicists that we really use mathematics to see the world. Because for us, mathematics is in fact a sensory perception organ. It's the way that we see the world. It's not just writing something on paper. It's a way for us to see parts of the world that you can't see in any other way. Well, if you see the world with equations, there's an interesting benefit. You gain godlike powers. Now, that's not godlike powers in the real world, but it's godlike powers with respect to the equations in the world that you are studying. And so you can change those equations at will, because the laws of mathematics are actually fairly flexible. And so let's change the equations that describe electrons so that we change their spin from spinning at 1/2 h-bar to 0 h-bar, and let's see what happens to this atom when we do that. So here is normal behavior. Now we're going to change the spin, and you'll notice all the electrons collapse to the lowest level. Well, boy, we're glad that doesn't happen. Because you see, if that happened, there would be no chemistry. And if there was no chemistry, there'd be no biology. And if there were no biology, well. And so our very existence is partly derived from this very strange property of matter, that we can split matter and look at things that spin at 1/2 rate, or we can think about particles like the photon, which are in fact force carriers, because the photon is the carrier of the electromagnetic force. And all those things have this property that they're called bosons. You can pass them right through each other. So these are properties of our universe that we see in everyday life. Let me talk about another interesting property of our universe, and then we're going to start to move on to the realm of why we want something like the LHC, the Large Hadron Collider. In fact, let's go and talk about the LHC just for a second. Here's a picture I drew from the web, I downloaded from the web of the LHC. This is looking down on the border of France and Switzerland, looking at the city of Geneva. And you'll notice that red ring that's drawn in the picture. That's a picture of the Large Hadron Collider. It's about 27 miles around. It's buried underground at about 150 feet. And it will be used to cause protons to collide with each other with more energy than our species has ever been able to produce in such an experiment. That's the Large Hadron Collider. Now, it's going to be the most powerful device of its type in the world. Right now, if you ask about a similar device, we Americans have this device. It's at the Fermi Lab in Chicago. It's a collider which does essentially the same thing. Now, the Large Hadron Collider, or LHC, is going to be much more powerful than the device in Illinois, which is called the Tevatron. And so what's called the energy frontier, that means the place where the highest energies in collider physics have been studied, is going to move from the United States to Europe in the year 2007 with the completion of the Large Hadron Collider. This is the first time in 50 years that this statement's been true, that the energy frontier will not reside in the USA. Now, what about you Texans' part in this story? Well, back in the 80s and mid-80s and the early 90s, you Texans in your foresight were supporting the construction of a laboratory in Waxahachie, Texas, just a little piece down the road. And this device was called the Superconducting Supercollider. And what the Superconducting Supercollider would have done if we had gone ahead and built it was to take protons and smash them together, much in the way that we saw these pictures of fermions trying to collide. And when you do that, some interesting things happen. When you cause like-charged objects to get very close to each other, you increase the amount of energy. But according to Einstein, remember Uncle Albert gave us this crazy equation, E equals mc squared? It says that energy and mass are equivalent. So when you cause objects to go close together and increase their energy, some of that energy can in fact be converted into matter. And in fact, it does become matter. But it doesn't have to become the same kind of matter with which you are familiar in your everyday experience. It can become new forms of matter. And that's what the Superconducting Supercollider would have done for us. It would have allowed us to have energies about 3 times as powerful as the LHC in order to probe what kinds of matter can exist in our universe. Now, the SSC wasn't built. It's not coming back. It'll never come back. It had a stake driven through its heart. So I'm not here to lament the SSC, but I am here to tell you what our nation decided to forego with the decision not to build the LHC. We have, however, supported experiments that are situated at the LHC. In fact, the U.S. has spent about $500 million building detectors in the laboratory in Geneva, Switzerland, that will fit inside of this ring in order to observe what happens as these one-third as powerful collisions occur. And we think some interesting things are going to occur, and that's the bulk of my talk. Now, the SSC died, and there are lots of statements about why that occurred. One is that it was too pricey. There were cost overruns. But I like to remind people that the complete SSC price was about the price of 4 B-2 bombers. So we could have actually easily afforded to build the SSC. There were other dynamics at work which explain why we didn't build that device. But we have the LHC, and my community is excited about the LHC because this will be the place where we will be allowed to probe the universe at scales looking for new forms of matter that we have never seen in the laboratory before. So let me tell you about some of the things that we're worried about. So we'll talk about this one first. Remember earlier I showed you these bubbles that represent protons and neutrons? Well, here's another one. And you'll notice the 3 balls inside. Those are the things that are called quarks. And so in this movie, I'm going to imagine, remember, because I'm talking about mathematics and every picture I show you is actually a set of equations, I can manipulate those equations for you. So I'm going to manipulate these equations in such a way that I try to pull this bubble apart. So first I'll let it bounce around, and now I'm going to grab the 2 ends and start to pull. And in fact, I did so, as you can see, by grabbing the two quarks at this end and pulling in this direction, and grabbing one quark and pulling it in that direction. In fact, you can see that one quark sort of right there. So I'm pulling this bubble apart. Now this bubble you can think of as a proton, because a proton is in fact a collection mostly of three quarks. And so I continue to pull it apart, and you can see it stretching. It continues to stretch. And now, just like a rubber band, when you pull a rubber band, you increase the amount of energy that's contained in the rubber band. Ah, there's that word energy again. And so what did Uncle Al tell us about energy? E equals mc squared. And so some of this energy that's in the pulling, and let me back this up just a little bit for you. You'll notice right here where I have just succeeded in pulling the bubbles apart. If you count the number of quarks, it's not the number that I started with. In fact, there are the two that I started with here. Here's the blue one that I was pulling apart, but right in the middle, there are two new quarks. Where did they come from? Well, it's exactly E equals mc squared work. The energy that was there in stretching the bubble out has now been converted into new sets of quarks. And now that these quarks exist, I can let the system separate, and as you can see, instead of having one proton, I now have a proton and a particle that we call a pi zero. Now, equations have told us about these kinds of processes for about 20 years, and we would like to test these things. And so that's one of the purposes of a machine like the LHC, to see if this picture that I have described for you in terms of a set of equations is actually the way that nature works. And we can do this more accurately at the LHC than any device in the world. Now, you might wonder, well, why would you care about that? Well, you see, understanding nuclear energy is actually an important thing. You know, we have problems with radioactivity. Eventually, we would like to solve these problems. One possible way to solve these problems might be to figure out how to turn the radioactivity off. You can't do that unless you actually study nuclear energy. And so we actually have the cure to pollution. People often say science causes pollution, but you see, science will also be the cure. Because you're not going to stop this, you're not going to decrease pollution by not doing science, because you won't have the capabilities to deal with the pollutants. Whereas science offers us exciting possibilities about gaining control of these things that are so dangerous. So that's one of the things that we'll be studying at the LHC. Let me tell you something that's really weird about our universe. In our universe, there are four forces. They are the electromagnetic force. Well, gee, that's what makes our beepers and cell phones work. There's a form of nuclear energy called the weak nuclear force. Now, when I give talks to the public, I try to remind them, oh, you know about the weak nuclear force already if you're my age. Because in the 1950s, there were lots of science fiction movies about mutants and monsters, and they always glowed in the dark because they were radioactive. Well, that glow is not science fiction. It's actually science fact. Radioactive particles actually do glow in the dark. And one of the processes responsible for that is something called beta decay. And beta decay is in turn caused by the form of nuclear energy we call the weak nuclear force. Now, there's another form of energy that actually keeps those quarks in the interiors of the bubbles. That's called the strong nuclear force. It's a very different sort of thing. And so in nature, we know about the strong nuclear force. That's represented by this dot here. There is the weak nuclear force represented by the green dot. There's the electromagnetic force. Then there's the weakest force of all, the force of gravity. Now, if you actually did an experiment, you would find out that this is, in fact, the way the forces arrange themselves. The strong nuclear force is the strongest. The weak nuclear force is actually next, then electromagnetism, then gravity. Except that the forces are actually very funny. If you go to a pool, a local pool, if you know how to float, you can sort of lay there in the water and have a nice, relaxing time. But if you were to go to the Great Salt Lake in Utah and try the same thing, you would find that you float higher in the water. And the reason you float higher in the water is because there's a lot of salt dissolved into the Great Salt Lake. And salt water has a higher density than pure water. There was this famous story about a guy who jumped up out of a bathtub running around yelling, "Eureka." His name was Archimedes. And the story goes, when Archimedes figured out why things float, he was in a bathtub and he jumped out excitedly, ran out of the house with no clothes, and tried to explain to his neighbors, yelling, "Eureka." Well, the point of that story is that the way things float, he really did figure out. And it depends on the density of the liquid. In fact, there's a very simple equation we physicists know how to write. It says the buoyant force is equal to the density of the liquid times the acceleration of gravity times how much liquid you push out of the way. That's what the equation says in words. But this example of the two forms of water show that the force laws can change. The force law for the Great Salt Lake is actually bigger than the force law for the pool of water. And so sometimes forces can change. And it turns out that these forces, these fundamental forces in nature, show exactly the same behavior, but not with respect to salt, but with respect to the energy at which you study the systems. When you study systems at increasing energies, the electrical force actually increases. We can see that. The electrical force in my drawing is the one right here. So let me tell you the whole story. The strong force actually decreases. The weak nuclear force actually somewhat decreases. The electromagnetic force increases. And so you find out the forces look like they're going to converge. Now, this kind of behavior, the fact that the force laws actually change with respect to the energy where you study them, was discovered about 15 years ago in a set of equations in a paper by Steve Weinberg, Howard Georgi, and Helen Quinn. It's a very famous part of physics, a result in physics from my part of physics. We call this the running coupling constants. Now, this running coupling constant is something we want to study in the laboratory because, once again, we can make these kinds of predictions, but we want to know, is this how our world works? Now, let's imagine that you have even more energy. What do you think is going to happen here? Well, let's see. Well, let me back this up a bit. If you'll notice, the weak nuclear force and the electromagnetic force coalesced and became a single force with the same strength. That's called the Electroweak Transition. And we know that it's real because we can see the evidence of this already for the past 10 years in a set of experiments that were conducted at the old accelerator at CERN. But when we work to higher energies, we expect that there will be another joining, where the strong nuclear force, the weak nuclear force, and the electromagnetic force are joined together to be a single kind of force. Now, you'll notice that gravity is left out of this picture. It's still separate. And finally, if we can work to higher energies, well beyond the energies of the LHC, we expect ultimately the gravity force would join the gang. Now, this kind of behavior, as I said, we've seen in equations. And we've measured a little bit of this sort of running of coupling constants at the tevatron. That's part of what the tevatron does. But you see, at the LHC, we're going to be further along in these curves, and we're trying to check to see whether this prediction has anything to do with our world. When you're at low energies, you're back over here. When you're at high energies, you're getting closer to the places where interesting stuff is going on. And that's one of the purposes of the LHC, to study whether these unifications will occur. If the SSC had been built, we would be studying these questions here in Texas. That's what we lost. That's one of the things we lost when we decided not to go forward with the SSC. There are other things. Let me show you our universe in toto, or at least partially toto, and it's not the dog. In our universe, there's the electron. There's a particle in nature that's 200 times as heavy as the electron. It's called the mu particle. And then there's a particle in nature that's 1,700 times as heavy as the electron. It's called the tau particle. Now, the interesting thing about the mu and the tau is, except for their weight, they behave exactly like electrons. In addition to the electron, there are lighter particles called neutrinos, the electron neutrino, muon neutrino, and tau neutrino, which are very similar to electrons if you could turn off the electrical charge. We talked about the quarks. Well, the quarks, which are those little pieces of matter that sit inside the bubbles, there are 6 of them times 3. Because remember the 3 colors we had? So there are up and down quarks, there are charm and strange quarks, there are top and beautiful quarks. And they come in colors, blue, red, and yellow. So 6 times 3 is 18. There are the force carriers. The force carrier for the electromagnetic force is the photon. For the weak nuclear force, there are 3 carriers. They're called the intermediate vector bosons. And they won a Nobel Prize for a number of physicists. First, Weinberg, Salam, and Glasgow in the end of the 70s for writing the mathematics that predicted these objects. And then later for experimental physicists who actually saw these objects in the laboratory. For the strong nuclear force, there are 8 objects called gluons. And now this, by the way, this table, which you can find in many physics departments around the country, is our generation's version of Mendeleev's table of chemical elements. I mean, you've all walked into a high school and see that chart that has H over in one corner and HE over in the other. That's from the 18th century. This is what 20th century physics has brought us in understanding the structure of the universe. So it's a sort of complicated place. And now some interesting things are the following. Remember that property of self-repulsion I talked about on the electron? That is shared by everything in these 2 columns. They all have that same rate of spin. They are all intrinsically self-repulsive. On the other hand, everything on this side of the transparency has that property that if you turn off electrical charges, they will pass right through each other. They are bosons. And so now we see a very funny dichotomy in our universe. We see a dichotomy where everything that is like the electron and self-repulsive spins at the same rate, whereas things that could pass through each other spin at a different rate. So is that a necessary condition for our universe? Well, back in 1977, I was rather 75. I was a graduate student at MIT, and I was looking for a thesis topic. And I studied the physics literature, and I noticed that there was a piece of mathematics that made a prediction the likes of which we had never seen before. And this prediction is that it may be the case that that table that I showed you is not all there is to our universe. Let me reassemble that table for you really quickly. That's what we know about our universe. That's what was on that chart. We see the quarks here illustrated by red blocks, up, down, charm, strange, top, and beautiful. We see the electron neutrino, the muon neutrino, the tau particle, the tau neutrino, and then we see the force carriers. We have the Z particles, the W particles, the gamma, and the gluons. Those are the things we saw on that table. Some additional objects I've added because it turns out that wave that I showed at the beginning of my talk about the wave of gravity, well, that says that the gravity is carried by a kind of particle too. That particle is called the graviton. If you're a Star Trek fan, you've heard about gravitons. They talk about gravitons all the time in science fiction. But Einstein in 1916 made the prediction that these are real things, long before anyone ever dreamed of Star Trek or Star Wars. And then finally in nature, there's this weird object we believe out there called the Higgs particle. We've never seen the Higgs particle in an experiment. We would like to see it, and that is also a second major goal for the kind of physics I'm talking about here. If we had had the SSC, we would have gone looking for this other object. It's predicted to us by a funny piece of mathematics that I'll talk about in a moment. In fact, let's talk about it right now. Why do we want the Higgs particle? Well, this is a diagram that you'll find in many physics classes called the Mexican hat. And the way that it works is as follows. Mathematically, we can describe an object called the Goldstone boson, which kind of sits at the top of a hill. When it is at the top of this hill, the photon, the Z particles are all massless. And now, as the Goldstone boson falls down the hill, you can see what has happened is that the Z and W particles have gained mass. Here we represent that by having the balls grow bigger. But the photon gains no mass at all. Now, it turns out that this funny picture that I showed here is a set of equations, and it's the only set of equations our species has ever discovered that allows us to understand why the W and Z have mass, and we have seen these two objects in scientific experiments for over a decade. So we know they're there, and we know they have mass. And yet the only mathematical description that allows for that to happen includes this picture, and this picture then predicts this thing called the Higgs Boson. So that's why we, in our picture of the universe, we had this one object that we had never seen in the laboratory, but that we sure would like to see in a place like the SSC or the LHC. Now, remember our running coupling constants? One of the interesting things about that chart is that they didn't all join at the same time. What happened was that the weak force and the electromagnetic force, they joined first. And then the coupling constants continued to run, and then the strong force joined them. And then finally, at the very end of that process, the gravitational force joined them. That was that little movie we saw. Well, suppose we don't really know as much about the universe as we think we do. And in particular, in this self-repulsive stuff. Suppose it's the case that there are things that like electrons, but if you turn off their charges, they would pass through each other. Suppose there are things that are similar to photons that if you turn off their charge, they bounce off of each other. Could our universe be like that? Well, this is a question that I started asking in 1976 when I was a graduate student. There was a piece of mathematics that had been discovered about a year earlier called supersymmetry. And what it predicts is that sometimes you can find things in nature that have the attributes of electrons but can pass through each other just like photons. It made a prediction that there are things in nature that have attributes of photons but bounce off of each other just like electrons. And these other things are called superpartners. Now, superpartners would be new forms of matter and energy that we've never seen before. So let me assemble them in our little drawing. So here's ordinary matter. There's the Higgs particle. And now if these superpartners exist, they're kind of a mirror image, we believe, of the forms of matter and energy that we know. So for example, the electron, which occurs here, would have a superpartner called the selectron. The photon, which occurs here, would have a superpartner called the photino. The up quark would have a superpartner called the up squark. The Higgs particle would have a superpartner called the Higgsino. The graviton would have a superpartner called the gravitino. Now, so about 20 years or so, my community's been playing with this mathematics. We've seen these things in the mathematics. And so the question is, do they occur in our world? Now, why should you care about that? Well, in the 1820s, there was a guy named J.G. Stoney who was an electrochemist. Nowadays, people don't think about electroplating, but back in the 50s and 60s, we used to have big cars with chrome-plated bumpers. And these bumpers were plated, so electroplating was a big deal. Now our bumpers are all plastic mostly, but in those days, we had these metal bumpers with shiny stuff that was just stuck on it. Well, electroplating had been around actually for over a century, and J.G. Stoney was an electrochemist back in the 1820s, and he understood that, I can understand how electroplating works if there is in nature something that is lighter than the electron, than the atom, and it also carries charge. He was the first person to have this idea. Later, he named this something. He called it the electron. And so here we see that when someone thinks of a new form of either matter and energy, 100, 150, 200 years down the road, that can have profound implications for science, technology, and ultimately for the way human beings live. So if these new forms of matter and energy exist, then 100, 150, 200 years from now, someone may be talking about a neat piece of technology, and you might ask me, well, what might that be? Well, I can't really tell you, but let's use science fiction. Maybe it's a transporter. Because you need something, if we're going to have things like transporters, that's not going to work with the equations that we have now. Something new has to change in the equations. These are new things. And so this opens up possibilities that I cannot tell you what they are, but I can look backwards and tell you how this process works. Now, these superpartners are really interesting because they alter the business of the running coupling constants. So here's our picture of the coupling constants once again, at low energies. If these superpartners are there, they're going to change what happens. So let's set this in motion. And you can see already what's happening. You'll notice the strong, the weak, and the electromagnetic couplings join at the same place. So one of the interesting things that even if we don't see the superpartners, if we can watch how the ordinary forces change with energy, watch the tracks along which they follow, we can detect the presence of these superpartners. And then once we know that these superpartners are there, then all bets are off in terms of someone finding a new technology based on these things. That's how science works. So at the LHC, the search for supersymmetry is going to be a major task. We will either detect it by watching these running coupling constants to see whether it's this path that nature follows, or whether she follows this path, where the two join first and the strong forces left out. Supersymmetry, all three things join at the same place. Without supersymmetry, two join first and two are left out. And so it's by following these tracks that we are most likely to see the superpartners. Now, the other way that we might see the superpartners is if nature's very kind to us, their masses will be such that we will directly produce them in the collisions of the protons that will occur at the LHC. So that's why my community comes to you periodically and says things like, can we have a few $1 billion? Because that's what we do when we come to the American public and say, high energy physics needs multi-billion-dollar instrumentalities in order to study the structure of matter. This is the set of questions that we are pursuing. Without your support, without the support of American citizens, we are not, as a nation, going to pursue this. And as I said, we have already ceded the energy frontier to Europe. Now, it's not that I'm a nativist, because I tell people all the time, I don't think America should be about throwing walls up and saying the rest of the world cannot compete with us. In fact, I think of that as very un-American. You know, Americans love to play games. We love our football, our baseball. Boy, do we love football in Texas. And not necessarily Major League football, high school football. I mean, what West Texas town would be respectable without a football team? We love games in this country. We love competition. We must show that same love for competition in the pursuit of science and technology. Because if we do not, our future as a nation will look considerably dimmer than it has been for the last 50 years. It is going to be the American people, I think, and I hope, that will demand that our nation continue to pursue science at its very boundaries, for the very simple reason that we Americans want the future to be at least as bright for our children as it has been for us. So the Lords of the Rings that I'm talking about are you. You're the Lords of the Rings because you're the ones that will make sure that we Americans continue to pursue this physics. Thank you.
There are microphones. There are two in the front and one in the back if there are any questions from the audience.
I think they've all become experts.
Jim,
Yes.
what sort of tests will the LHC do that will, specifically the experiments and whatnot, that'll shed light on the supersymmetry?
The experiments that are most likely to do that, as I said, are the ones where we trace the paths along which the forces are either decreasing in the case of the strong force or increasing in the case of the electromagnetic force. If we can get an accurate picture of those paths as we move to higher and higher energies, that's the most likely thing to tell us that supersymmetry is going to occur in nature. And for people like me, boy, are we going to be happy, because it means that I didn't waste 30 years. Yes.
What path in physics today do you think presents the best attempt currently at quantizing gravity?
Ah, that's a different talk. The question was, what path do I think represents the best attempt to quantize gravity? I don't know if this gentleman was setting me up or what. There's only one answer I know to that question. It's called superstring theory. I, in fact, spend a large part of my time working on this. Many of you perhaps saw the video on PBS called The Elegant Universe and heard what I had to say there. Many people watching my comments there think I'm a skeptic, but I'm not. It's not that I'm a skeptic, it's just that I'm a scientist. You see, for those of us who are scientists, we understand that at the end of the day, no matter how pretty an idea is, it must occur in the laboratory. When I teach a physics course to my students, my freshmen, one of the first things I say to them after I fill up a board full of equations is, that's not physics. Physics is what happens in the laboratory. And so to quantize gravity, we're going to have to, the only mathematical way forward is that I see is through superstring theory. However, I don't believe that the current conventional view of superstrings is going to survive. In fact, one of the things that string theorists often tell the public is there are all of these hidden dimensions out there. Well, maybe. During the middle to late 80s, 3 different groups asked the question, if we never see these hidden dimensions, does it mean that string theory is wrong? And all 3 of us, and I was one of the groups, came back with the answer, no. It turns out string theory can exist without hidden extra dimensions. It's just that the mathematics of these things is significantly more complicated than the mathematics considering higher dimensions. And so I am, in fact, an enthusiast about string theory. However, I think we need to apply the same rigorous standards to probing this as our community has for the past several hundred years in defining the difference between science and mythology.
I suppose the coalescence of the forces at higher energy will tell us something about origins in the Big Bang and
absolutely. Absolutely.
How the
In fact,
out.
yes, the comment is that as we watch these forces merging, will it tell us anything about the Big Bang? The answer is absolutely. Part of the reason why my community studies this kind of physics is that we've realized over the last decade that by doing this physics, we are also looking at the history of our universe. For example, in our universe, there was a time when light could not pass freely through the universe. It was kind of like an opaque, milky substance. As the universe continued to grow and expand, at one point, light suddenly could travel freely through the universe. This occurred at what has been called the first dawn. And just before it occurred, light scatters off of something called the surface of last scattering. This surface of last scattering lets the photons travel freely. In the 1960s, our species first detected these photons. We now call this the cosmic microwave background. And the cosmic microwave background is the best scientific evidence that we have that a Big Bang occurred. You see, the cosmic microwave background is as if a snapshot was made of our universe when it was 300,000 years old, and we can go and look at it. This is an amazing development, that the universe has a picture of itself as a baby.
if it is possible to pull apart a quark, to pull apart a subatomic particle to generate more quarks, would it be possible to combine subatomic particles together into one to generate more quarks?
Oh, yes, that happens all the time. In fact, that's the process by which our energy the sun derives its energy, is in fact the fusion of subatomic particles. And when you do that, you actually get a net increase in energy. So that's how thermonuclear reactions work.
But does that still create more quarks inside the...
No, the fusion typically does not. The question was, can you imagine a process where you combine nuclear matter together, and what that does is create an increased number of quarks from the system that you started from? And my answer is that ordinary fusion doesn't do that, but we do have examples of that in mathematical equations where you get what are called exotic hadrons out. So yes, that happens, we believe. Yes, there's a hand here, I believe. Well, if you read the Long Island newspapers a few years ago, you'll know that there was a scare that some people were saying that these colliders might create black holes and then Long Island would get sucked into nothingness. That's exceedingly unlikely. Look, there are dangers associated with this. The devices where this kind of physics is done are multi-million-dollar devices on the order about $250 million, 4 stories tall, with tons of lead, incredibly high currents, some things that if you were to touch, you would instantly be electrocuted. Yes, all of those dangers are there. And then, of course, they ultimately are also radioactive after long periods of running. So yes, those dangers are all there. Unless we risk them, we won't get the knowledge. And I think one of the defining things of our species is that we're hungry for knowledge. There's a hand here.
One more question. Your graphic on the supersymmetry
Yes.
implied that there was one supersymmetrical particle base in the graphic. If there were a multi-dimensional space, could there be more supersymmetrical particles?
Well, first of all, you don't need more dimensions to get more supersymmetric particles. As I said, I'm really talking about equations. I know variations on these equations where for every one particle you get 2 supersymmetric particles, or for every one particle you get 4 supersymmetric particles. Those kinds of equations have been what I've been studying for the last 30 years. So yes, they exist. However, the model that I showed you is what is the consensus of my community, is the most likely way nature will use this piece of mathematics. Yeah, well, I'm not sure I know very much about it either. There was another hand here. Well, because another thing that I didn't show because we're limited in time is the way we did. The question is, how will you know if you created these new super partners that I showed with the 2 halves of our universe? And they're not really halves, they're because that's about 5% we think of what's really there. But anyhow, the answer to your question is that the way we detect these particles is essentially by looking at what are things that are called particle tracks. And these objects will generate tracks unlike those of an ordinary matter particle, and that's how we would know. That's why we study the mathematics, because it makes predictions about what the patterns will be.
Sir, I have a question. It is generally believed that human beings are facing an energy crisis.
Yes.
And what would your comments be that in future, how will we cope with that? And would LHC be responsible for more pseudoscientific kind of ideas like zero-point energy and cold fusion that could come out of it?
Well, the part of your question asking whether the LHC would be responsible for more pseudoscience, I don't quite understand, because that was created before the LHC. So there are people who run around and say things like 0-point energy and what have you. We are facing a number of crises, I believe, as a species. You spoke about the energy crisis, but at least as great is global warming. There are recent reports that the rate of melting of ice at Antarctic has probably gone past the tilting point, where in fact the ice will continue to melt and thereby raise the level of the seas at an accelerating rate. That's certainly a crisis. We face the crisis of pandemics. There's a possibility that bird flu will mutate, and Lord knows that if that should occur, we may be subject to something that our species has not seen since the great influenza pandemic that occurred at the end of the First World War. So there are lots of risk out there. A meteor could come and strike us tomorrow. We're not really better than the dinosaurs, I don't think. All of these risks are out there. The one thing that I think that our species can do to protect itself is to pursue science in the interest of our survival, in the interest of a sustainable human society. That knowledge is not presently in our grasp. Things like the LHC, if properly used, may give us the keys to this sustainable human society. We must succeed, I think, at this goal. Otherwise, I fear for our species.
Dr. Gates, you just said properly used. How will the experimentation at the LDC, how will that be distributed out to the physicists on this planet that want to conduct experiments? Will they submit proposals? Will they have to pay for time within the accelerator? How will it work?
Well, physics has, first of all, been an international globalized activity for about a century and a half. Unlike lots of the world, we've lived in a globalized world for a very long time. The way that physics disseminates its information is by having physicists interested in that science become part of the experiment. In the U.S., if you ask about this science, there are two parts of your taxpayers' dollars that go to support this science. One is through the agency known as the National Science Foundation. The National Science Foundation makes grants to university professors who are interested in studying this kind of physics. This is sometimes called blue sky physics, because there's no obvious application of this other than the information and knowledge that comes out of it. The other part of your government which supports this kind of science is the Department of Energy. And in fact, the Department of Energy's support of this is about 10 times as great as that of the National Science Foundation. So the scientific community, those of us who are interested in this, will continue to the data, by the way, is posted online. That's something else that people don't seem to generally understand, that scientists, and certainly in my community, we were the first people to actually use well, first of all, my community created the World Wide Web. Bill Gates didn't do that. A lot of people are confused about where the World Wide Web came from. It came precisely from particle physicists who wanted to be able to show these kinds of pictures and equations and data to each other, and they developed the World Wide Web. That's where it came from. So we've always been about having open dissemination of our information. And unless somehow this becomes involved with concerns of terrorism, I hope that our community will continue to do this.
How were the original quarks made from the Big Bang?
Well, the Big Bang itself, the question was, how were the quarks made from the Big Bang? The Big Bang itself in physics is the most energetic event that we can conceive. Accordingly, there was a lot of energy around, and if Uncle Albert got it right, just having the energy there is sufficient to create mass. In our equations, and this is in the realm of what's known as relativistic quantum field theory, this has been understood since the 1950s. So it's not a question about how it's done. We had a mathematical explanation. I can't give you any words. This is where my analogies fail me. If you ask me in detail, I would say, give me about 5 or 6 years of teaching you physics. Yes, sir.
One of the major discoveries in astronomy in the last few years has been that the universe is expanding at an accelerating rate.
Yes.
And the concept of dark energy has sort of been invented to try to explain that.
Yes.
Could you talk a little bit about how the concepts of dark energy and dark matter fit into what you've already talked about?
Thank you for setting me up on that question. I'm trying to get my computer to respond. Hang on a second. When Albert Einstein wrote his equations in 1916, he found out something very interesting. His equations for the gravity also made predictions about how to describe our entire universe. He didn't set out to do it, but they're there. And when he first wrote the equations, he got what you see in these first two pictures here. There is a parameter in Einstein's equations called the Cosmological Constant, which in his initial work he set to 0. And if you do that, what you find out is that the equations predict that there's an event that we call the Big Bang, and the universe expands afterwards at a constant rate. And this picture assumes that the most of the energy at the instant of the Big Bang was contained in matter. If most of the energy was contained in the gravitational field, then subsequent to the Big Bang, you would expect a big crunch. So this is Albert Einstein circa a little bit after 1916 and his initial creation. But in 1916, it was the consensus of the world's greatest astronomers that we live in a universe that is static and eternal. Well, so Uncle Al had a problem. I like to say Albert Einstein was at least as bright as our brightest physics students. And if you watch physics students in an experimental course, you'll find out just how bright they are. Because often they do experiments, they record data, and they know what the answer is that they're supposed to get, but the data doesn't quite support it. And so they introduce this thing called, it's a very technical device. It goes by the name fudge factor. Well, Albert Einstein knew how to introduce a fudge factor, and so he did. He introduced a fudge factor, and in his equations, if you tune it just right, you find out that it gives you a static universe. And for most of 60 years after that, for a few years after that, he was happy. But then a guy named Hubble came along with a few other people and said, that idea of a static universe has been blown up because we can see the galaxies rushing apart. And so at that point, Albert Einstein, at least the story goes, declared this his greatest blunder and quietly erased this term for his equation. This situation stayed that way up until about 7 years ago, when we started looking at the explosions of stars that are called type 1a supernovae. And when you study a particular type of type 1a supernovae, the way the light comes out is very characteristic of something we call a light curve, and we can use that to then measure how fast the universe is expanding. And so that was the genesis of the universe seems to be speeding up. So if we live in a universe that seems to be speeding up, interestingly enough, that's this middle picture, it turns out the simplest way to do that is to go back to Albert Einstein's original idea of the cosmological constant. Now, he wanted it to be negative to hold it to the universe static. But if you make the constant positive, what it does is create a universe that comes into existence and then speeds up, and that's what we think, that's the best explanation we have for dark energy, that it's actually the effect of of a slightly positive cosmological constant. Now, what does a cosmological constant mean? Well, like charges repel. You're very familiar with that. When there's a cosmological constant, it means space repels. So if you have a bit of space in one place and another bit of space separated, with a cosmological constant, they push each other apart. Well, you might ask, well, what's in the middle? More space. And you get a speeding up of the expansion. And that, we think, is the source of dark energy. That's our best explanation right now. Now, you guys know that he and I discussed this beforehand, so I could bring this up for you. Yes, ma'am.
I have a question. You alluded to the fact of lost scientific research to other countries, so loss of American research. Recently, there was an article in a popular news magazine also describing an exodus of the scientific community from the United States to the areas where the climate was more productive. Have you seen that in your experience? Is it a crisis? And if so, how can we stem it?
The crisis is not here yet, I believe, but I think I have seen its avatar. On the 20th of December of this year, I went to an event in Taiwan. In fact, let me show it to you. This event was called the International Young Physicists Symposium. There were young people from 21 countries, 110 of them. The youngest child was 10, the oldest was 17. And these are young people who are excited about physics. This, for example, was one of the signs that greeted the participants at this meeting. And let me also show you the total conference. As you can see, there's a familiar face here in the middle. And also, let me show you the U.S. ambassadors. These two people here were forced to be there. They're my twins. They did a project on diffraction of light. Made their father very happy. But the thing that I came away, I came first away from that excited that so many young people are interested in science, in particular in the science, the kind of science, not the specific science, but the field of physics. And I saw an excitement, a joy, an expectation. And that encouraged me about the future for our species, because I think science is very important for our future, as I've alluded several times. But with further thought, I became very, very worried, because I compare that love of science in these young people to what I see among American youth, particularly in my own community, the African American community. And I don't see the same level of expectation, dedication, a sense of joy about doing science. And if our nation has lost that, we will see the effects of that in about 50 years. We will have lower rates of increase, or perhaps stagnation, in standards of living for this country. That's the thing that's frightening to me. I wonder, where are American kids in this thing about doing science for the future? I don't see it often. That's the frightening thing for me now.
Thank you.
Yes?
Hello, Jim.
Would you care to speculate a little bit about the 95%?
Yes, I can do some speculation. This will take me back to superstring theory, interestingly enough. Those two halves that I showed you, ordinary matter and superpartners, the equations that make those predictions are in fact not the equations of superstring theory. They're the equations that are of a truncated version of superstring theory, something called supergravity, or rather the supersymmetric minimal model, standard model. If I turn the full mathematics of string theory on, what I can tell you is that those two parts there are, in fact, a very small sector of a much larger part of a set of equations. Now, these other sectors of the equations, we don't really know very much of them, except that I can tell you that, roughly speaking, this ratio about 5% looks to be about right. We think that this 95% of, someone asked me about dark matter, because that's in fact what we're talking about. This 95% of this stuff that's out there, and in fact, I should probably show you the effects of that stuff. Boy, you guys are good. It looks like I'm having some, I'm having some software party problems, so let me just stop this. But basically, the point I was going to make is that if you believe in string theory, then this idea about 5% is about right. And this other stuff is going to be exceedingly difficult to understand, I believe. But we can see its imprint in the equations. So, like I said, it seems like it's probably there. There was someone standing over here.
Hey.
Calling Jim.
Hey, how are you, Jim?
Hello, Mark.
I wanted to ask you about the super partners.
Yes, sir.
Effectively, how could one actually get a signature for, say, for example, the electron superpartner in a laboratory? What would be, for example, the telltale signature?
Let me try to bring up something that comes close to. I'm not going to be able to answer that question exactly, but let me try to answer it pretty closely. And again, I'm tied to my technology here, so I'm hoping it's going to support this. Well, it looks like we're making a little bit of progress here. This is the picture I wanted to show you. When you look at an experiment like the Superconducting Supercollider would have produced, or the LHC, what you get out are patterns that we call tracks. So here's an example of a set of tracks. It turns out that the shape and the form of these tracks depend on the properties of the things that are producing them. And in fact, for superpartners, they produce tracks that are unlike anything else that we know. So the actual detection of them will be to look for one of these unusual patterns that's predicted by our equations, much the same way that Maxwell predicted the waves that Hertz found. So it's looking for an unusual track in the experiments. Yes, sir?
Where does antimatter come into all of this?
Well, in some sense, from the very beginning, antimatter, again, is something perhaps you know from Star Trek, but antimatter was in fact not invented by science fiction writers. The original construction of antimatter occurred in 1928 when a physicist named Paul Dirac wrote an equation that had the following properties. He wanted to write an equation that was consistent with Einstein's relativity. He also wanted an equation that was consistent with the laws of how small things move. Small objects do not move like baseballs. They have an entirely different set of rules called quantum theory. And so Dirac wanted to have a set of equations that obeyed both. He succeeded in finding an equation that was consistent with these two sets of rules and described the electron. But he also found there was a second solution to this equation. This second solution was unlike anything anyone had ever imagined. It's an object that looks exactly like the electron, but it has the opposite charge. That was the initial introduction of antimatter in the human consciousness. Now, it turns out that Dirac's equation describe things like electrons. In fact, remember when I talked about the quarks and the leptons? They were sort of up to the side. Every single one of those things obeys Dirac's equation. Anything that obeys Dirac's equations has antimatter automatically. I finally found my dark matter slide, and I'd like to run through that. I'm not sure. We'll see what happens. Imagine that you were God, meaning write some equations. So let me write some equations where I do two things. You might not be able to see it here, but what I've done here is I've set up some equations where I've set a plane of stars. So I've laid them out like on the surface of a square table. I've done that up here. It's even more difficult with the lights to see it here, but there's also a similar array down here. So imagine that I take this square table with the stars laid out nicely on it, and I take the table and I twist it, and then I walk away. What happens? Well, that's over here where you can see on the other side. So I twist the table. As you can see, the stars start to clump together because they feel the gravitational attraction of each other. And very quickly, if you watch this upper drawing, you realize there's something very interesting about this, because these are just equations running. This begins to resemble the spiral arms of our galaxy. Now, that also happens down here, but if you watch this part up here, you'll see a disaster occur. The galaxy starts to fly apart. And the reason that it flies apart is that even if you calculate the total gravitational attraction up here, the galaxy is not stable on timescales that we need to explain the existence of our galaxy. What's different about this bottom picture? Well, you'll notice it's slower in evolving. The reason is because in this bottom picture I haven't shown you, but I've included about 9 times as much invisible gravitating matter in this calculation, and then that stabilizes the structure of the galaxy over the timescales that we need to explain our existence. And so one of the things that dark matter seems to be there for is to stabilize our home so that it doesn't go flying apart. So this is one thing that we're really confident about dark matter. There's another set of observations that have to do with watching the rates at which stars in a single galaxy rotate about its middle. And again, that answer is consistent with 9 times as much dark matter, meaning matter that does not shine electromagnetically, being responsible and playing a major role in the rotations of single galaxies. So that's dark matter, and why we're pretty convinced that it's there. And we think it may be something to do with this extra stuff coming from string theory.
Our universe seems to have presented us with an experiment that started with very high energy and small items and going to low energies and very big, which gives us a trajectory through that multidimensional space that's kind of a line. Your equations, being God there, gives you some freedom to get off of that line. Might we find some interesting things? I'm sure you've already thought about it.
Well, in string theory, in fact, there are groups of people. You're talking about a single line. That sort of does describe our universe, but you're wondering, can we get off of it? In string theory, we have found evidence that the answer is yes. As you run the equations of string theory, you find out that you can deviate from the lines that describe the history of our universe. And we think, we're not sure, but we think that our universe, at least in terms of these equations, is a part of a larger structure that's been named the multiverse. And the multiverse means you're off of the lines of our universe. So yeah, we have mathematical reasons for believing in that possibility. Yes, sir. Oh, sure. The question is, what happens to these new particles? These new particles have incredibly high masses, about 1,000 times the mass of ordinary matter. Nature has a law that seems to be pretty universal. She likes for things to be at their lowest energy state. According to Einstein, high mass means high energy. But if nature wants things to be at lowest energy states, it means that these high mass things have to decay back into ordinary matter. So it's sort of like watching a wave. You know, if you watch some waves collide on the surface of a pond, they come together, then they reach an incredible peak, but that's not sustainable. and the water relaxes back down. The analog of that is we create these very massive particles, but they're not sustainable by the laws of nature, and they decay back to ordinary matter. And that's what, by the way, produces these unusual tracks that I was talking about to the young man over here.
I've heard there might be a theory that the speed of light has changed.
Yeah.
Can you explain that? And is there any evidence or anything?
There's no evidence that I know. Can I explain it? Well, it's still in the stage of equations, but let me just say that, look, theoretical physicists, we lie a lot. We don't mean to, but we do. Because, you see, the universe is an incredibly complicated place, and because it is so complicated, we have to essentially try everything that we can think of in our imaginations that might be an element of our reality. And then we ask our experimental colleagues to test these ideas. Now, this idea that the speed of light is variable is something that we know how to, in fact, incorporate into equations. Look, we theorists can do just about anything. But this is not a widely accepted theory that the speed of light is variable. But, like I said, it can be done. Thank you. Uh-oh. Yes, sir?
Back to the laboratory. I haven't heard what the latest word is from these gravity wave facilities.
Ah, yes, the gravity wave facilities, LIGO. Well, actually, about maybe 4 months ago, I was walking through the airport at Baltimore Washington International Airport. And coming down the hall, I recognized a familiar figure. His name is Rainier Weiss. Ray Weiss is the father, one of the fathers of these facilities. Ray Weiss has been thinking about these things since the end of the 60s. And so I saw him in the airport, and I'm like, Ray, what are you doing here in the airport? And he said he had been at a series of meetings in Washington. He was on his way back up to MIT. He's a professor at MIT, by the way. Emeritus status now. And I said, so what's going on with LIGO? And he said, well, first of all, the National Science Board has recommended that we go to what's called Advanced LIGO, which is an upgrade of the facility that would almost definitely let us see these waves. However, Congress has never allocated the money for the upgrade. So the machines are there, we're tuning them, and then he told me something very exciting. He said, even if we don't get the upgrade, we're learning how to operate these devices in a better and more efficient manner. And within 2 years, we may actually have a chance to do some science with these things, to actually see gravity waves. So the people who are pushing it, who are Kip Thorne at Caltech, Ray Weiss, who used to be at MIT, there's a whole community. By the way, one of those members of that community is sort of right here, this guy, because he's done work in gravitational waves. The LIGO science community is continuing to push this boundary and making this effort to find these waves, even without the upgrade that they need, that would really make it go. There's one more hand. Yes, much like the speed of light may not be a constant. And again, like I said, we know how to lie about that too. So yes, we know how to change equations to make that a true statement.
Unfortunately, that's all the time we have for questions today, but we have a reception which is starting in a few minutes that's going to be in the garden room, which is on the first floor on the other side of the atrium. So Professor Gates will be there, and if you have any other questions or anything else you'd like to discuss, then we will be there. Thank you for coming.